Okay, I think everything is ready. So, okay. Hello, everybody. This is Luboš Pirkl from CFD Support. Welcome to the webinar on Turbomachinery CFD, which is a CFD simulation workflow for all standard rotating machinery. The test case for today will be a radial compressor. Just in case of any technical problems, feel free to contact me. We will answer all your questions by email or something. So the webinar is going to take about 1 hour. In the first part, I will show how to simulate the compressor in Turbomachinery CFD. In the second part, there will be a Q&A session dedicated to your questions and my answers. Feel free to put your questions below to the comments, or there is a special Q&A window where you can put your answers, and I will answer them later in this webinar. I will share you my screen now and start with presenting. So I believe you can see my desktop now. Here is the Turbomachinery CFD graphical interface. This is how it looks like before we come here. Maybe I will give a brief description what Turbomachinery CFD is. So I'll go to my web browser and start from our website. So you can type Turbo Machinery CFD, and very at the top, Turbomachinery CFD from CFD support is the product website. Okay, so Turbomachinery CFD is a unique software based on OpenFOAM. It was designed for CFD simulations of all standard rotating machinery, such as pumps, fans, compressors, turbines, water turbines, both radial and axial machines, both compressible and incompressible flows. Let me put just a quick review of its unique value proposal. So number one is Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever and use it for unlimited number of users, jobs, or cores. And obviously that gives their investment in Turbomachinery CFD a permanent value. Number two is Turbomachinery CFD is fully automated, which means all the workflow from the start to the final results report can be run by a single command or a single click. Number three is Turbomachinery CFD is open source. That makes it easily customizable to your own purposes, to your workflow you're familiar with. So it's extremely customizable, extremely flexible. Number four is there are real tutorials included, so the user has no doubts about the best practice settings. So there are real machines included that are already preset. You can basically take one of them, replace the geometry, and modify the settings and run. There are many other benefits of using Turbomachinery CFD. I'm not gonna go for all of them. Feel free to contact me, and I will gladly answer all your questions in detail via email, or we can call sometime. Yeah. So perhaps the most important information from today's webinar is all the information is available online on our website, CFD Support. So I have pasted some major links below to the comments in this webinar. So you can watch from there. You can browse our website. Yeah, Turbomachinery CFD is available both for Linux and Windows operation system. Turbomachinery CFD is very transparent. There is a trial version available for free for 1 month period of time, so anybody can try it. and afterwards he or she can decide to buy or not. So it's very transparent, and clients have all the information before they take any decisions. So it's very clear, very transparent. We answer everything in detail. Also, the project is open source, so you can read anything. Yeah, so anybody can download it in our download section from our website. Download software. There are two versions available for Linux and for Windows. So, for example, in Windows, a little bit more popular than the Linux. You can read everything. You can put your email, download the file, the installation file. There is a PDF called Start Step by Step, where you can read everything, how to install, how to run your first case, simply everything. So yeah, I believe this is very transparent. I'll go back. So this is how it looks like. This is the Turbomachinery CFD graphical interface. So the Turbomachinery CFD workflow is fully served from graphical interface. It has its GUI. The graphical interface is the paraview. So it's basically a set of plugins to paraview. You can work from this GUI. You can also work from terminal, but the most of people prefer to work from graphical interface. The decision is always on you. The decision is taken by our clients. More people use Windows version. In today's webinar, I'm gonna work from Windows. Also, the Linux is the same workflow, so everything is the same in Linux, by the way. Okay, so perhaps it's time to start working now. So maybe I should show you. We will deal with the Radial Compressor. So there is a tutorial which you can download also from our website easily. You can click download test cases and then cases, and then the Radial Compressor tutorial. Typically, the aim of the compressor designer is hunting for the pressure ratio, flow rates, torques, and of course the compressor efficiency. Each Turbomachinery CFD simulation has its data inputs, and those are the configuration file or the configuration setup in a graphical interface, and the surface model. The surface model is something which comes from the designer, which is the machine which is gonna be tested, and then its settings. So basically, the Turbomachinery CFD workflow is handled by CFD processor. CFD processor reads the input and does everything. It does pre-processing, processing, post-processing, and also the technical report with all the results. Okay, so I'll go back to my case. Yes, so the configuration file is plain text file. Maybe I should show you at our website. There is a well, yeah, of course it's here. And Turbomachinery CFD, you can click Turbomachinery CFD workflow example, where is all the important information written and with some examples. What is important? The configuration file is simple text file where where you can specify all the simulation features. Where is the, for example, where is the surface model located, how many processors, how many iterations, how many points, how many speed lines, what are the velocity, what are the physical properties, what are the all those constants and settings. That's the configuration file, and then there is a surface geometry. That is the input. Maybe I can show you very from the beginning. So I start from very from the beginning. I'm in Total Commander, so I will jump somewhere very to the case, the radial compressor. So you always start with opening the file, the configuration file which has the extension TCFD, like Turbomachinery CFD. So I have my file, which is the standard tutorial radial compressor .tcfd. I can just press enter on it. It opens in ParaView, and it gives me basic settings. So the ParaView can read this tcfd file, and on my left-hand side bar there is everything, all the settings. So what type of machine, where the file is located, and then I'm not gonna go one by one. There's all the settings. Perhaps during today's webinar we will speak about it, but for now, just general information. There is uh, all of the settings in graphical interface. So you stay all the time in the graphical interface. 100% of the workflow is served from the interface. So once the Turbomachinery CFD TCFD file is read, you press apply, then it's read. Then you can see all those settings, or you can modify all those settings. You can watch your surface file, and then you can specify how many speed lines, how many what are your boundary conditions, of course, how many for example iterations, what are the stop criteria. You specify anything, and once you're satisfied, you can then important step is to run the TCFD manager, which is special filter. It's here, like icon with arrows, and also it can be searched from the filters. It's a special filter from ParaView, which handles all the simulation. So you can load it and press apply. Then the Turbomachinery CFD manager, the simulation manager, is loaded. So you have your file, Radial Compressor TCFD, with all those settings. Then you have Turbomachinery CFD manager, which is a special filter where you can say you want write down your case. You can specify the name, or you can leave the default settings and you will get the default name. So I say write my case. So the case is being written down. Basically, it's standard open form case, of course, with special boundary conditions, with special settings, with special function objects, and I would say hundreds of special tunings from CFD support to make available running Turbomachinery machines. Okay, so you write down the case, and then you can decide what to do. You can go manually, you can create the mesh, you can run the calculation, you can, of course, you can once you're satisfied with the results, you can skip to the next point anytime. You can abort the calculation. You can write down the current results and then abort the calculation. What is really important, each simulation has its very detailed report. and it can be updated anytime. So once you simulate, you have your report, and anytime during the simulation you can click in TCFD Manager, you can click to update report, and your report with results is updated. You can do it anytime. So depending how many speed lines you have, how many points you have, you can watch the results which were computed till this time, and the report is very detailed. There are many statistics of the simulations, of time, yeah, all of them, residuals, flow rates, also the efficiencies, how they developed in time, how they're standing against the flow rate. The same with torques, total pressure differences, which is important layer, and that's the pressure ratio basically. What are the total pressures per interfaces? That's important. How your total pressure is spent when going through your machine. The same with velocity magnitude. You can watch how your velocity magnitude is developing via interfaces. By the way, I will look if the broadcast is running. So you can hear me. Okay, I can go ahead. Okay, so there's the velocity magnitude, and also there are special evaluations at the interfaces, the circumferential angles and meridional angles for really detailed oriented machine designers. You can see what are the angles, the average angles at every interface, and you can, during the simulation, you can update the report anytime, watch the results. You can stop the simulation, you can rerun the simulation, you can change the settings, go back. Really, it's really comprehensive in this sense. After the simulation is finished, you can do the visual post-processing. You know the efficiencies, you know all the statistics, you know torques, you know pressure ratios. Then you can do a special visual post-processing which is called TurboBlade Post. It's again a set of plugins for ParaView where you can watch, for example, the meridional averages of your machine. Yeah, the meridional average of the pressure, for example. Yeah, and for example, blade to blade, which is again quite important at any level between hub and shroud. You can specify you want to see how the flow is. How is your flow developing? You can see stream traces via surface lit filter. You can see separations. You can see how smooth is your fluid flow anywhere in your machine. So this is really also quite interesting. Of course, any variable is possible to view. So yeah, this is the this was the general introduction. So I'll take a look into my notices. What is quite important to say. Yeah, so the process is automated. So you can run the TCFD manager. There you can run clicking the run all. You can run all the process, and then you wait for the results. You get the information when the simulation is going to be finished. Yeah. So the most easiest way how to simulate your machine is simply to take the, I will show you on our website. The most easiest way how to simulate your machine is to take the tutorial. Yeah, is to take the tutorial in download. In download cases, there are a couple of tutorials. So this is the Radial Compressor. So the most easiest way how to simulate a compressor is to take the tutorial, download the tutorial, which is pretty simple. You can say, okay, I want to download the tutorial. It gives me the tutorial. It's compressed in zip. You can download it, extract it, and then you open the TCFD configuration file, and you can replace the geometry which is specified in settings. You can replace the geometry in the settings. So you can say what's your inlet, what's your outlet, what's the, for example, when speaking about the impeller component, you can it's better to specify what's your hub, what's your shout, what's your blade, what are your blades, and you can go one by one in the settings. Yeah, that's pretty obvious. If you hesitate, what the settings, what's the meaning, for example, what are the physical dimensions, you can watch the configuration file manual, where is the basic explanation, what's the physical meaning, what are the other options you can specify. But practically you stay in all the time in the paraview, in the graphical interface, in the Turbomachinery CFD, from the beginning to the final results. You can save everything, of course. You can really do the save data, save Turbomachinery CFD setup to the new setup. You can get back anytime, so you can very easily save the configurations with some plain text file and use them anytime in the future. You can get back. So it's really smart in this way. Okay, I'll go. This was the general introduction. I'll go back to the okay, yeah, still here. Okay, I'll go back to the Q&A and take a look. And I have to say, I cannot see any Q&A, any questions, right? So there are any questions? There are no questions here. I can also take a look. Give me a second. Okay, I can show you. Maybe that's the best way. I can show you what I see. Okay, I'm gonna show you what I see, and it's this. This is what I see. Well. No. This is well, yeah, the webinar. The webinar is here, and I have to say I cannot see any questions here. There are some. Well. Okay, no. There are no questions here. I will take a look to my email. Okay, there are no questions here. Okay, so what I will go ahead on my own. So I'll go, yeah, maybe a little bit. What I can do is showing, okay, for example, the post-processing, or will I? Okay, so there's the, okay, I can say a little bit about the meridional average, which is I can show you what it is. Sometimes rotating machine designers are interested how particular field, for example, pressure, is spent when flowing through your machines at the impeller, for example. So this is there is a special filter which is called meridional average, which is applied on volume field. That's important. It's always applied on internal mesh, just the internal mesh. Everything has to be switched off. So you can apply this filter on internal mesh. It's now you can see it's alive, so I can click it, I can use it. I did it already. I have used default settings, and it gives me such a plane, this plane, which is, yeah, it's obviously the meridian, a simple plane, flat plane, a meridian of the machine. Maybe I can switch. Can I do this? I will try, and maybe I should make this transparent, so 0.2. Okay, here you can see that's what I'm speaking about. That's my machine, that's my compressor, and this meridian is the average. You can see that's the average of all the values, like circumferentially averaged. So okay, yeah, that's the meridional average. Of course, you can see any value. So, for example, total pressure is well, okay. The clip. I can take a look. What's the total temperature? Okay, not very interesting. For example, what's my velocity? Okay, perhaps the relative velocity. Okay, and yeah, total pressure, for example, how it is developed in the meridional view. What is also important is the blade-to-blade view. So you can do the transformation, which is called turbo unwrap. Again, the special filter for ParaView, which is called turbo unwrap, and it can yeah, it can do a special transformation. Your impeller can be transformed to the like hexahedron, and the intervals are like 1, 1, and 2p. And in this transformation, you can see for any quantity, any field, you can see it's plane anywhere between hub and shroud. So this is important. So this is, for example, 50% plane between hub and shroud, and yeah, and yeah. So this is the relative velocity. You can, using this relative velocity, you can see how the fluid flow is flowing. Especially important is how the flow meets the leading edge, and how it leaves the trailing edge in the impeller. What's the angle of attack, especially at the close to the tip. Yeah, what you can see is, yeah, any quantity, of course. So you can go for the pressure, for example, total pressures. Yeah, all the quantities. It's pretty lot of them. Okay, so that's the blade to blade. Yeah, anywhere. Yeah, any plane between hub and shroud. Where am I? Okay, I'll go back. I'm sorry. You can, yeah. So I'll go back to my to the webinar, which is here. I'll take a look. Okay, so Debasis Panda is asking, hi Lubos, will you share this webinar via YouTube? Yes, I will. So hello, hi Debasis. We have met. We made some discussions in the past. Yes, it will be shared in the YouTube, so you can view this webinar via YouTube. I will do that. You can. Is the link? Okay, yeah, it's the second last answer. So there's a link where you can see the YouTube channel where this video will be uploaded just soon after this webinar stops. So that's the question from the from the webinar, and I'll go back. Yeah. I say stop sharing my desktop. Which brings you to me. Hi, I'm here, still here, and yeah, and and then there are some questions here. Okay, Mr. Pirkle, you mentioned the software usage won't be limited by core number. How about its capability in calculating several parallel simulations at once? Can it work in HPC with hundreds of cores? Abdul Rahman Hassan. Abdul Rahman, yes, it's not limited at all. At all. No limits at all. So you can have 100 sessions, 100 cores each, and it's no limited. So we take a client, for example, the Hassan company. We sell the software to you, and you have no limitations at all. Really, no limitations, and you can keep the software forever. Of course, the time for which the software is updated and maintained and supported, that we provide extensive support. So there are sitting experts here behind this wall, and they're really masters of their branch, and they support you. They support you until your technical support is valid. So but the software is you can keep the software forever, and there are no limits on it. Yeah, so that's the Hassan's question. Casey Park. Hello, Casey. Yeah, pleasure to meet you. See you again. Yeah. Can you explain the format of the input geometry in detail? Yes, Casey. Okay, let's spend some time there. So I'll go there. So I'll go there. So I'll share you my screen now. Sharing. Okay. Yeah. So yeah, basically. So in OpenFOAM, in any CFD, I'll start from the beginning, from the beginning. So in any CFD, especially in OpenFOAM, you never start from the scratch. You always need to grab somewhere which is working, which is similar to your case, and modify it. That's how it works. That's how people get results. You never start from the scratch. So if you're interested, if anybody's interested in simulating a compressor, do the following. Of course, you need to have some version of Turbomachinery CFD, perhaps the demo or the paid version, and download the tutorial. You should start from the tutorial for sure. So download the tutorial from our website and then modify it. You can load the Turbomachinery CFD configuration file, which is file.tcfd. You load it in ParaView, and you are here. You have these settings on your left-hand side. Just forget this right-hand side. You see everything here in your left-hand side. So here's the menu, and here's the full configuration. Everything is here. Here is some general settings where your configuration file is located. What's your machine type? What's your coordinate system? Yeah, so origin is any point of axis of rotation. Axis is the directional vector of axis of rotation. So basically this configuration says, coordinate system says, what is your axis of rotation, and you can see it's the z axis, because point 0, 0, 0 lies on line which has the directional vector 0, 0, 1. Okay, so your the axis of rotation. You can say I will scale it. So you might have your model in millimeters. Then you say my scale factor is 0.001, because you OpenFOAM in general works always in SI units, right? So you need to go in meters. So you can go in millimeters, but you need to scale them to scale your model. Yeah, feature edges. Yeah, it's a special option for us. Yeah, I'm not gonna comment it now, and not very important for the beginners at the beginning. Physical settings. You can use the gravity. You can use, okay, so it's obvious. You can go compressible or not, or incompressible. Use specific your dynamic viscosity, which is physical property of any fluid. You can say what's your reference density. Again, that's a typical property of any fluid. Reference pressure, reference temperature. What's your fluid? What's your molar weight? What's the heat capacity? And the physical settings. Now the speed line settings. You may say how many speed lines you want to simulate. So you might be interested in 1 or in 10 speed lines, which is the speeds of rotation. You can say how many speed lines. We have 3 speed lines. Each speed line has its rotation speed, of course, in radians per second, or it can be in rounds per minute, of course. That each speed line may have any number of points, right? And each point has its number of iterations. The number of iterations, it's the option which may not be necessary reached, because there's also auto stop mechanism. And I'm not gonna go very much to the details, but there's auto stop mechanism, so you can specify the conditions at which you are satisfied with your results, and you want to skip to the next point. I will go ahead. Inlet boundary conditions, of course, yeah, you can. So we recommend to compute such a compressor with total pressure at the inlet and fixed static pressure at the outlet. Again, you specify the boundary conditions for each point, and yeah, those are the boundary conditions. The simulation settings. Yeah, of course, number of processors. There are some limits on your fields, on your quantities that may help you for some unstable setups. It might be useful to keep you robust. Yeah. Numerical order. Yeah. Convergence check, auto stop, bind to core. Those are really like special. We can not very important. Initial conditions are not very important. Yeah, and this is important. Components, right? Components. So this particular case has 4 components. It has 4 components. You can see 4 colors. Each component is 1 color. So component 1 is the impeller, and it has inlet patches. It's just one, and it's called rotor inflow. Outlet patches, it's single one. It's called rotor outflow. There may be any number of them, so you can overweight. Like you can have 10 inlet patches, so you can put 10 inlet patches. But anyway, inlet outlet. A hub is something, yeah, which is the wall close to the axis of rotation, the shroud, and blades. You can of course you can add like suction side, the leading edges, trailing edges. You can add caps. You can add pressure sides, suction sides, and even many of them. You may specify, is this component rotating? Yes. How many averaging planes do I need here? Background mesh size, this is very important, because here you say I want to have the basic cell would be 3 millimeters. That's very important, because this influence the size of the mesh, and the size of the mesh in a big way influences the time, or the overall time of your simulation, right? So this background mesh size is very important choice, important parameter. Very carefully with it. You need to get somewhere the internal point, which is any point from the inside of your component. The component should be waterproof. Ideally, it should be vertex to vertex. You may specify the wheel diameter. It's not even mandatory, but you can. We like it. We like to have it there, but it's more comprehensive. You know more information about your machine. Yeah, and you can have cylindrical background mesh, which is and there are another options. If you click this gear wheel, you can see any components might have many other options, which is basically most of them are mesh settings. I'm not gonna go for those details just today. Maybe sometime later. Maybe we can. Okay, so I'm going back to the webinar. Uh, can you explain the format of the input geometry more in detail? Okay, Hi, Casey. Yeah, again, the same again. That's what I did right now. Okay, another. Okay, this is Casey. Hi, Lubos. Hi, Casey. Okay, it goes. Hello, can I use the mesh from other softwares like ISM CFD, for example, TurboGrid from ANSYS? If it is possible, what would be the format to export? Alex. Hi, Alex. Thank you for this question. I like it. Yeah, I will answer it. Okay, so I'm going to the it would be the easiest way how to answer this question would be to come back to the so Turbomachinery CFD as it is now, it does not allow automatically read external meshes. It will be in the next version, so it will be part of the next version. I believe in September or October we will release new version. There will be included this feature. We are working on it currently. So it's not possible directly, but you can do it in this step. You can write the case, right? You can write the case, which writes the case, and instead of creating the mesh, or you can create the mesh in SnapHex Mesh, and then you can replace manually. So you can add external meshes, you can, but manually. So you write the case, create the mesh, then you replace manually in the, I can show you, I'll go to the total commander. So this is the case, what I did this morning. Maybe I can show, okay, this is the case I've showed you just a second ago. You would need to import your new mesh to OpenFOAM. By the way, you asked about the format. So the MSH Fluent format is the best. The .msh extension is the best one. We have great experiences. You use special utility which is Fluent 3D mesh to foam, and it should be ASCII, not binary, but ASCII, and it usually works very well. You can rename things, and put them into yeah, the mesh is not here, but okay, I can show you here. So in constant, right? It's the open form. So in constant, in polymesh, you can put the mesh here, and the rest is the same. Then you go back and you say, I want to run my calculation, and everything is the same. You have all the features, the full report, all of them. So yeah, so MSH manually. In the next version, in the very next version, we will yeah, okay. I'm back. Yeah, so yeah, it will be yeah. MSH is the answer, and manual in the next version it will be automatically. There will be special option where you can specify it's MSH. These are the names of my patches, because that you need to merge, right? Because yeah, and what's the hub, what's the shaft, what are the blades, and etc. What is the inlet outlet, and then it's gonna be there. So in the next version, okay. Okay, currently, okay, done. Yeah. Okay, so I have to say I can't see any more questions and reminders. So I I will ask you to put them if you have any, and I'll go to the webinar. Yeah. I can't see any questions here. I'll go take a quick look into my email. Not there. Okay. Okay. So I think this is it. I think I think this is it. Yeah, this is it. So thank you for your time. Thank you for your attention. Please send me anytime an email, give me a call. Anything is waiting for you. It's transparent. We feel ready to tell you, to tell the world out loud that we are here. We have great software, and we are ready to show everybody it works. It's extremely effective. It's extremely affordable comparing to what's available in the market. So we believe this is a really big thing in the world of CFD and numerical simulations of rotating machinery. So thank you for your time, and yeah, bye bye. Yeah, see you next time. See you next time. Yeah. Okay. And here I say stop the broadcast. Yeah. Okay. Bye.